Here I'm going to show you one way of finishing off the proof of the inverse function theorem, and I'll do another way in the next video and maybe make some final comments. But the first way comes back to one of the very first things I was talking about is practical ways of solving y equals f of x, finding a solution. It's you create h sub y of x, that's the badness, in the least squares sense of how close you're getting with f of x to y, and you want to minimize that. And ideally, you'll find that its minimum is 0. Well, let's just run with that. Again, there's a formula. We can do some calculations. We can manipulate, and then we'll see where we get stuck. So here's a little exercise. It's a version of maybe the very first exercise I gave in I think the first video. Show, instead of talking about the gradient, I'll talk about the matrix of derivatives of this guy. It's a function to r, so it's basically the gradient. But so show that the derivative of this guy, evaluated some x, okay, that's a row vector, a matrix, or a transformation from Rn to R. So we need to put something into it, let's say v, is equal to minus, let's see, y minus 2 from the square here, times y minus f of x. That's a vector dotted, as in the dot product, with d f of x, that matrix, acting on v. So the hint is this is the dot, this is y minus f of x dotted with itself. That's always how you want to write this guy when you do any kind of algebra on it. And not a too hard application of the product rule and the chain rule gives us this. Okay, so let's suppose this is equal to 0, right? Because that's what we do to find a minimum of something in calculus. We take the derivative and set it equal to 0, and we slide it over so you can see the 0 there. Okay, well, when is, and this should be 0 for all, well, so that's the end of the exercise. Now we're looking at 0, want 0 for all v. Equals 0 for all v, okay. Well, if that's going to be 0 for all v, well, let's for a second assume that that gives us all possible vectors here. If I've got this vector dotting with every single vector to be 0, that means y has to equal f of x. Okay, so let's see. Is that really true? If I put in all v here, am I going to get all possible v's out here? Well, let's see. So let's assume here that df of x, we actually don't have to really assume it's invertible anymore, is onto. Okay, so, and I'll formalize this in a minute. We're still kind of playing around with stuff. And this makes sense. It shouldn't really be necessary at this stage in the proof to worry about df of x, the derivative map, being injective, being one-to-one, because we've already dealt with all the one-to-one stuff. All we want is the locally onto part. That's what this is about. And so it really only depends on the derivative being onto at this point. But if it's onto, then if I put in all possible inputs here, it's going to give all possible outputs here, all possible vectors in Rn. And the only way that this vector, dotted with any possible vector in Rn is going to be 0 always, is if this vector is 0, in other words, y equals f of x. Okay, so that's good. So you might think we're done, because we certainly are assuming this throughout. We're assuming it's actually invertible throughout. So there we go. The calculation is the only way you get a critical point is this is 0. But remember, when you're doing a max-min problem, there's two kinds of max-min you could get. There's a critical point, and then there's a boundary value. Okay, so that's going to be important. Alrighty, so we need to set things up, and we're going to have some things to make more explicit. We need to show that hy does have a minimum. Not every function has a minimum, right? Because remember, we're interested in just an existence proof here. We're not, even though I talked about relating it to very practical problems and sort of computational solution methods, we really just want to show that this works, period. Okay, so we need to show that hy does have a minimum, okay, and that minimum is not on a boundary. Well, boundary of what? Well, okay, so we really does have a minimum on some set k, which we're going to have to create, and that it's not on the boundary of k, to be more explicit. Okay, there's a reason I'm calling it k here, is because by far the simplest way to be able to assert that some continuous function must have a minimum is to make sure that this is compact. And K is often a letter for compact because it's German for compact. Okay, so this is just generalities about having minima. This will be some careful geometry. And then, given that, that means that the minimum, which we're going to show does have to exist. If it's not on the boundary, the minimum is a critical point. And voila! That means y equals f of x by the calculation we just did. It means, in other words, that given that fixed y we use to create the function hy of x, there is an x that gives the critical point, and that must mean it gives the minimum of this guy. Must mean hy equals f of x. And that's what we wanted to show. Okay, so let's see if we can create that k. And the geometry that's going to be necessary for this is one more use of locally by Lipschitz. Okay, so let's see if I can be a little more efficient on paper here. I can really use the bottom of this guy, I think. Ignore this little stuff at the top. Okay, so what's the situation? We've got our function f from u over to Rn, and here's x naught, here's y naught that we're nearby to. Okay, and we need to find some little neighborhood that gets hit. But first, let's remember that we know that f is locally by Lipschitz. That's a very powerful geometric condition. Okay, and so there is some v, okay, where f of x1 minus f of x2 is greater than or equal to some c prime sub v times the distance between these guys. Okay, for all x1, x2 in v. Okay, so to be even more geometrically precise, let's just inscribe a little ball in here. Okay. Random, wiggly open sets are not incredibly great when you're trying to do careful geometry. Let's say this guy, since it's open, it contains some b x naught r. Okay, so we're just going to let r be so that it's Lipschitz with this known interior, Lipschitz constant, the lower bound Lipschitz constant, c prime. Okay, so in fact, we just really need it on bx naught r. Okay, and then the only other thing we're going to use is that df of x is onto for all x also in this ball. We really are assuming it's onto everywhere in U, but this is all we need. So remember, the derivative being onto sort of infinitesimally means it's trying to first order go in all directions. That should really make it fill out a nice little open ball over here. And that's exactly what we're going to see given this extra geometric information. Okay, so here's where I want to make it an exercise, because the rest of it is some fairly simple geometry. Let me just give away a little bit of it. Okay, so remember, we don't need to show that we can fill out some predefined big ball here. We get to choose how small the ball is. That was at R1. We get to choose, as long as R1 is greater than 0. And then we only need to show that we hit y's in that little ball. And it can be quite small. Okay, so let's choose R1 is 1/2 C prime times R. Okay, so C prime, the smaller C prime is, the weaker this condition is, the closer it is to failing. And so C prime, including C prime, is really important to get the right wiggle room here. If the distance between the outputs is actually only known to be greater than or equal to 1,000th of the distance of the inputs, then it's not really very certain that I can go very far out here before things screw up. But if I go out a distance r, then I really should be going here a distance even bigger than c prime r. And to give it an extra little wiggle room, we put in 1/2. Okay, so in other words, let y be in the ball around y naught, that fixed base point, with radius 1/2 c prime r. Okay, now here's the exercise to finish off the proof. Okay, what do we want to know? We just need to show that if K, our compact set, is going to be the ball around x naught with radius r, and then x is in the boundary of K, which is just the sphere, so we'll just call it the boundary of the ball, then we want to show that hy of one of those guys can't possibly be a minimum for hy on this set. Well, the easiest thing to do is to show that it's actually greater than or equal to hy at the center. If it's greater than hy at the center, then it certainly can't be a minimum because the center is a better candidate. That's not saying the center is the minimum. It probably isn't, unless f of x naught is also equal to y. It's not going to happen. But at least that excludes the possibility that x is actually a minimum on the boundary. So remember, what we're trying to show is that these guys, when I map these guys over, those should go far enough away from y naught that they can't possibly come even close to hitting y. And therefore, something else in the middle must hit y. Okay, so let's see if I need to give you any hints here. I'm thinking. No, I want to leave it at that. Okay, the key is just writing down inequalities based on the Lipschitz and then some triangle inequality stuff. Okay, so let's recap what happens when we know that. This tells us that the minimum of hy cannot be on the boundary of this compact set. But what do we know has to be true for a continuous function? But hy from k to r is continuous on a compact set. That's short for compact. Okay. And therefore it has some minimum. If it's not a boundary minimum, then it must be a critical point minimum. And what did we discover? As long as df of x is onto, the only way you get a critical point minimum is if, in fact, your steepest descent algorithm has terminated and you've found it. You've nailed it. Okay, so the badness is 0. So, steepest descent in general could fail. Let me just show a picture here. Going back to some practicalities. If I have steepest descent, let me have some compact set k, and I want to find the minimum of some function. Suppose the minimum is here. So let me actually, in a different color, let me draw the level sets of this function. So here it's the hy function. So here's hy equal to c, all those level sets. Okay. I'm trying to get to that minimum that is really a critical point. And we know that if we achieve that, that's where the only way that happens is if you've nailed it with f of x equal to y. But what if the situation is you start out here and you start going perpendicular to those level sets following the gradient, and then boom, the smallest you can get on k is just because you've hit the boundary of k. And you're stuck, and you weren't nowhere near a critical point of that guy, and you can't conclude that y equals f of x. Well, that's what we wanted to avoid. We wanted to make sure that this is not the picture. We wanted to make sure the picture is more like this. Here's y naught, and here's the picture of the level set. So yeah, so here's, let me do this in brown again. So here's k again. We wanted to make sure that the picture for hy, the level sets of hy, is more like this picture, where if you start at some random point and you drive in, the only reason you're going to stop is you've hit the critical point. And that's a good thing, because that's where y equals f of x. Okay, so that's what that last exercise is intended to show, that doing a little geometry based on the locally by Lipschitz nature of f, that you're good. Okay, so that's really it. Let me just recap it one more time, though. Okay, we've now hit that last little bit. We now know f is an open map. That's interesting in itself, its local surjectivity, but that means it makes all the rest useful. All that local one-to-oneness, the inverses, all that stuff, there was this key hole in it that it might have been pretty meaningless if f wasn't an open map, but it makes all the rest useful, and it finishes the theorem. And I want to mention, in this presentation, I've been focusing on this Lipschitz stuff. Again, this intermediate stage between calculus and just are things continuous, are sets open, things like that. A little bit more of a hardcore version of continuity and one-to-oneness, the Lipschitz and the by Lipschitz conditions. And that came in even in this last bit, even though it was most directly related to f being locally one-to-one. It actually, and g being, and its inverse being nicely behaved, it actually came in the last bit as well. You don't necessarily see that in most proofs, but it was interesting to me when I thought about this, how much that condition comes in. Okay, in the next video, if you just want a full proof, you're done. In the next video, though, I'll go back to the other method of finding solutions, the second one I mentioned in the opening video, which is contraction mapping. And that's more likely the proof, that will emulate more likely the proof that you'll see in most books, except for in Spivak's book.